If we double CO2 from 425 to, let's say, 850, is it zero effect or it's just a very small effect? Doubling CO2? Zero.
It doesn't heat the surface of the atmosphere.
My guest today is Paul Linsay.
I was an undergraduate student at MIT. I went to the University of Chicago and I got a PhD in experimental particle physics. From there, I went to CalTech and worked on some experimental particle physics. During my stint at CalTech, I just got very tired of big science. It was large groups, lots of money, and long time scales. So I started looking around for something else. And then by accident, I bumped into a physics professor from MIT, Ray Weiss, who I'd known when I was an undergraduate. And he was starting up what eventually became the LIGO, the Laser Interferometer Gravitational Radiation Observatory, LIGO. You can look it up on Wikipedia if you want to get the correct spelling of all that stuff. It looked interesting, and it was basically benchtop physics. So I was going to be free of all the sociology or pathology of high energy physics. So off I went back to MIT, where I'd never expected to go again. And I worked on that for 10 years. Then CalTech was running a similar program in parallel. And about the end of 10 years, we thought that we would submit a joint proposal to the National Science Foundation for a full-scale observatory, which was a pair of interferometers, each one about 5 kilometers on a side. And of course, lots of money, lots of people, and lots of time, but I would be one of the bosses. Anyway, we submitted that to the NSF, and we got turned down. And at that point, I had to rethink my life because, as I said, I was going to repeat the sociology of particle physics. And who knew if we were going to get money in the first place, and then how long it would take. I figured it'd be 20 years to do it. So in the meantime, while I was doing the LIGO physics, I had taken an interest in chaos theory, nonlinear dynamics, and started doing research on the side. I had a grad student and some money. So I decided I'm going to get out of the gravity wave business, and I found that the director of the Plasma Fusion Center was interested in what I was doing. So I went over there, he got me an office, and I stayed there for about 10 years. And then one day, out of the blue, I got an offer from industry that my wife wouldn't let me refuse. So I left, at that point, I left 30 years of academic physics and went off into industry until I retired. So that was that. And though I did have one more contact with academic physics, this was 25 years after I had left the LIGO project. I met Ray Weiss by accident going to the hardware store on a Sunday morning where all good experimental physicists go. And he told me that they had got funded, they built a LIGO, and they had just detected a signal from the collapse of a pair of binary black holes, which is a very big deal. I congratulated him, and 2 years later, he shared in the Nobel Prize in Physics. Anyway, that was my last contact with academic physics. So later, I retired, and I needed something to do as a project. So climate science seemed interesting because of the physics, how does CO2 work? But that was a different part of the physics forest that I knew. So I was going to have to learn some stuff, which is always interesting. So I'd followed climate science as a tourist for a couple of decades, and I came to the conclusion that it's a con. Actually, those guys would have a hard time predicting high noon if you gave them an atomic clock. But even so, I wonder how they could claim predictions of 1 degree centigrade accuracy and a global average temperature when the local weather report can't even do 2 weeks in advance. It's also been puzzling to me how carbon dioxide, which only makes up 0.04% of the atmosphere, can heat up the other 99.9% of the atmosphere. So I thought it'd be good. It'd be an interesting science project. And while I was doing it, I realized that there's a lot of papers on climate history and radiation and climate policy, but none of them investigate the basic assumptions that go into the climate models. So this it motivated me to write the current paper, which is an in-depth analysis of climate model assumptions. It shows the climate models really go wrong. Okay, so these are the 3 major points I'm going to cover. A, the models make meaningful long-term predictions. B, the Earth is naturally cold. And C, the cold Earth can be heated, by greenhouse gases. All of these assumptions are wrong. Okay, now I'm going to do a slight diversion into nonlinear dynamics and chaos theory, which is very crucial actually to the models. So up on the upper left, there's a drawing of a little double pendulum. The upper arm is pivots on the ceiling, and there's a second smaller pendulum tied to the bottom of the first one. Now, this is an undergraduate physics student has no problem writing down the equations of motion for this thing, but you can't solve it because it's nonlinear. I won't go into details on what that means or how to do it, but in general, you can't solve the differential equations of a nonlinear system. So here's if you do a numerical solution, you can see that the thing just flips around all over. It flips all over, and you can see that it will sort of repeat itself if you watch carefully, but it'll never really come back to the same place. We're all acquainted with the weather forecasts on the evening news. They're good for a couple of days, somewhat doubtful for the coming week, and entertainment for 2 or more weeks in advance. The reason for this has been well known since the work of professor of meteorology Edward Lorenz at MIT in the 1960s to understand the limits of weather prediction. He called it sensitive dependent on initial conditions, also known as the butterfly effect. Butterfly flaps its wings in the jungles of South America, and 2 weeks later, there's a Category 5 hurricane that devastates New York City and New England. This is going on in the simulation, not in real life. It's caused by slight errors in initial conditions fed into the models, such as temperature, pressure, and so on. That's the butterfly in the jungle, these small errors. These errors inevitably lead to wildly different long-term predictions, even as the mathematical models are perfect, which is certainly not. Both physical systems and equations can be chaotic. In fact, this has entered popular culture. The mathematician in one of the Jurassic Park movies talks about it. The Chinese sci-fi books and series, The Three-Body Problem, depends on this. Newton figured out the two-body problem for gravity, the moon going around the Earth, the Earth going on the sun, and so forth. But the gravitational force is nonlinear and varies as the inverse square of the distance between two bodies. It gets weaker quite fast because of the square. It goes, if the force is 1, then double distance, the force is a quarter. That's 2 squared. If you triple the distance, it's a 1/9 as strong, and so on. Okay, the two-body problem is unique in that the orbits can be solved exactly. You get circles, ellipses, parabolas, and hyperbolas. Now, after Newton published this, of course, the mathematicians immediately tried to solve the three-body problem, the case of 3 planets or 3 stars orbiting around each other. Yeah, they worked at it, and then 200 years after Newton, the mathematicians gave up officially. There's no general solution. There are some special cases. The inability to make long-range forecasts is a classic example of what's now known as chaos theory, nonlinear dynamics, a branch of mathematics which applies to many physical phenomena, as well as mathematical equations and computer models, which depend on nonlinear forces. The weather and climate are well-known examples of this. Model predictions are only good a short time in the future, and they veer off into a plausible incorrect direction. In the case of weather, Lorentz figured out that to produce a good 2-week weather prediction would require covering the atmosphere with thermometers in boxes the size of a fist. And then you put thermometers in there and you go from there. In other words, it's never going to happen. Okay, now I just walked you through the double pendulum. And then the Lorentz had it started out with a modest 11 equation model of the atmosphere, and eventually worked it down into 3 equations with the interesting variables being called X, Y, and Z, very imaginative. And if you plot out, you started out and you plot out the motion of X, Y, and Z with time, you get this butterfly. The little dot is the position in time. And you can see that it goes close to where it was, and then it goes off in another direction. Sometimes it'll stay on one wing, and then it'll flip over and go to the other wing. You can't predict what it's going to do. You can predict for short periods of time if you have a copy of this thing and you put a dot next to it, see how they go. You can. It's actually a big deal on the web. If you look up nonlinear dynamics, chaos theory, especially if you look up the Lorentz attractor, you'll find just tons of papers on this. Wikipedia is a good place to start. You can play with all sorts of programs that are much nicer than this. But that gives you an idea how complicated it is, even though you think you can make a prediction, in reality, you can't. Now, the modelers understand that the models are chaotic. They admit it. The climate system is a coupled nonlinear and chaotic system, and therefore long-term prediction of future exact climate states is not possible. Rather, the focus must be upon the prediction of the probability distribution of the system's future possible states by the generation of ensembles of model solutions. So implicit in the statement is the belief that the computer models have some genuine predictive value, and they somehow bracket the actual climate so that the probability distribution is derived from physical states. Nobody says that the future possible states correspond to any genuine climate. There's no guarantee of that. And from what I understand, it takes them a year to run the one simulation. So they're never going to be able to figure out if they can actually do this. All right, on we go. Okay. The modelers also do not know how to actually write equations for many of the processes involved in modeling the climate. As a result, they resort to what they call parameterization. Again, you can look this up on Wikipedia. Wikipedia is climate model certified, so whatever you get off of them, they'll agree with whatever the latest is among the modelers. And here's a quote: parameterization is weather or climate in a weather or climate model is a method of replacing processes that are too small scale or complex to be physically represented in a model by simplified processes. Notice that they explicitly include processes such as clouds or rain that are too complex to model. Without experimental validation, parameterization is just guesswork and curve fitting. It's a black box. These are black boxes with lots of knobs that are used to add clouds and rain to the models. The state of the atmosphere goes in and clouds, rain, and still come out. For the uninitiated, a parameter in a set of mathematical equations or computer program is the exact analog of the volume control knob for an electric guitar. A parameter is just an adjustable knob, and it may even go to 11. Yeah. As the great 20th century mathematician John von Neumann once said, with 4 parameters, I can fill an elephant, and with 5, I can make him wiggle his trunk. It requires a massive leap of faith to think that the climate models have any connection to the climate of the Earth. All right, now I'm going to start going through the standard climate modeler's computation of the Earth's surface temperature. This is taken from a 1992 textbook, Physics of Climate by Picciotto and Oort. It's very important because it's the basis of all the climate models and the claim that CO2 heats the atmosphere. So as you can see, the Earth receives energy from the sun, which is absorbed by the Earth on a disk, which is the radius of which has the same radius as the Earth. Since the Earth is a sphere with a surface area that's 4 times the area of a disk, which you should know from high school geometry, the average amount of energy absorbed per unit area is 1/4 of the incident area, energy per unit area from the sun. They also reduce the incident energy by 32% to account for clouds, which is weird because Blackbody Earth has no atmosphere or clouds, but whatever. Knowing the radiation per unit area, one can compute the surface temperature using what is known as the Stefan-Boltzmann law. The resulting surface temperature is 255 degrees Kelvin, which is minus 18 degrees C, which is minus 0.0 degrees Fahrenheit. From now on, I'm going to be using Kelvin, which is the natural temperature with respect to absolute zero and how all temperature is measured in physics and chemistry. Okay, that's an aside. They can then claim that the average temperature of the Earth with an average temperature is actually 288 K, which is 33 degrees K more than the cold Earth, and the warming must be caused by the greenhouse effect of CO2. So we've got, in this one diagram, we have a cold Earth, and CO2 is the way it warms up. All right, let's do the next slide. Okay, now let's look at what the instantaneous sun. Okay, the problem is that the global average temperature is an unphysical concept since the Earth is a sphere. If it were true, the climate would be the same all over the Earth's surface. In fact, the winter at the poles is always winter, and the tropics it's always summer, and in the middle latitude, it's always the seasonal cycle of summer, fall, winter, spring, back to summer. By the way, global average temperature works for a star, which is a giant gas ball with a nuclear reactor built into its center. In fact, a lot of the stuff that the climate guys take was originally intended for stars. Anyway, okay. The issue is obvious by computing the instantaneous temperature over the surface as plotted in the figure. The temperature is computed from the Stefan-Boltzmann relation for a solar flux of 1360 watts per square meter. Okay, and you can see that the maximum is the maximum directly under the sun is 394 Kelvin, well above the boiling point of water. And then that's centered on the tropics. Then moving away radially from this point, it drops until you get to zero on the night side. Approximately 77% of the daylight hemisphere is above the freezing point of water at any point in time. Right away, there's no need for greenhouse gases to heat the atmosphere. Okay, the figure here on the right side, it shows the daily temperature cycle that you would experience near the equator. At 6 in the morning, it's dark. The sun comes up. At noon, it reaches maximum. 6 p.m. it goes to 0 again, and it just goes up and down like this. The lower green line, the thin green line, is the temperature that the previous approximation gave, and this is the freezing point of water. So you can see most of the day, the temperature is well above the freezing point of water. Okay, so now let's go. Let's continue. Okay, so this is a little more detailed calculation. Previous figure is an instantaneous snapshot of the Earth's surface temperature. The Earth, of course, rotates on its axis every 24 hours and goes around the sun every 365 days. This averages the incident solar energy on the surface, as can be seen here. The result is of a detailed calculation of the average solar insolation in every 1 degree latitude by 1 degree longitude cell of the entire surface, and including the daily rotation, the tilt of the Earth's axis, and the annual orbit around the sun. So the average temperature, which is calculated for this, is 267 Kelvin, not very far from what the back of the envelope climate modelers use. But notice that there's a very warm band around the equator, and the band between 33 north and 33 south is above freezing point of water. And then the minimum is 236 Kelvin at the poles, which gives a difference of 57 degrees Kelvin, hardly a uniform global temperature. Okay, I'm going to beat this whole thing to death. So next, let's go. Okay, now the Earth. This is a plot. I'm going to indicate what happens to the Earth's temperature when the tilt of its axis of rotation changes. It's another example of how the temperature distribution changes, even though the global average temperature from the back of the envelope calculation gives the same value for all 3 different tilts that I'm going to discuss. If a planet's orbital diameter is known, or Newton's law of gravity determines the length of the day of its year, and vice versa. This isn't true for the axial tilt of the planet with respect to the Earth's, with the plane of its orbit, which is random value for each of the 9 planets in the solar system, as is the length of the day. Different tilts produce different climates and temperature distribution. The figure shows the annual insolation changes when with the Earth's tilt of 22.3½ degrees. On 6/21, the summer solstice, the northern hemisphere is pointing toward the sun and gets maximum insolation. Minimum insolation is at December 21 in the northern hemisphere, when the northern hemisphere points away from the sun. And in the middle, on the equinox, day and night are exactly equal. There's 12-hour days. You can now, if you look at, this is a repeat of the temperature distribution that I showed you before. Okay. Now let's do Mercury. Mercury has the interesting property that its axis is exactly perpendicular to the plane of the ecliptic, the plane of the Earth's orbit. So day and night is exactly 12 hours each, all during the entire year. This gives rise to a temperature distribution that's very warm over a large swath centered on the equator, and there's only a very small cold spot at the poles. And again, the average temperature isn't much different from what the back of the envelope gives. And then one more to bore you to death with this. Neptune has the weirdest axial tilt of all. It lies exactly in the plane of the ecliptic. So at the summer solstice, the entire northern hemisphere is covered in full sunlight, and the southern hemisphere is in darkness. Then, as it goes around its orbit, of course, it comes to the equinox, and Dan Leiter's exactly 12 hours each. And then we get to the winter solstice. In this case, the southern hemisphere is in complete sunlight. Northern hemisphere is completely dark. And slowly again, as it rotates, you get back to the equinox. In this case, you get very warm poles and not too cold equator, but there isn't going to be a whole lot of sunlight there. It would be a bad place to grow plants, that's for sure. In any case, again, this has an average temperature that's not much different from the back of the envelope calculation. So in all three of these very different cases, there's significant areas of the Earth's surface where the average insolation raises the local temperature well above the freezing point of water. And there's no need to invoke CO2 to do the warming, even though these different axial tilts would produce very different climates, all of which would have significant surface above freezing. Standard back of the envelope calculation would be the same for each one. Okay, so the temperature of the Earth's surface. Currently, water vapor has, this is from the IPCC 2018, one of those monster books they put out. Currently, the water vapor has the largest greenhouse effect in the Earth's atmosphere. However, other green gases, primarily CO2, are necessary to sustain the presence of water vapor in the atmosphere. Indeed, if these other gases were removed from the atmosphere, its temperature would drop sufficiently to induce a decrease in water vapor, leading to a runaway drop of the greenhouse effect that would plunge the Earth into a frozen state. It's quite a statement. The greenhouse gases other than water vapor provide the temperature structure that sustains current levels of water vapor. Therefore, although CO2 is the main anthropogenic control knob in the climate, water vapor is a strong and fast feedback that amplifies any initial forcing by a typical factor between 2 and 3. Water vapor is not a significant initial forcing, but it's nevertheless a fundamental change of climate. So this conflicts with all the diagrams I just showed you of the insolation of the Earth as it actually occurs. I don't know why they haven't ever looked into this, but they didn't. So here we are. All right, let's do the next one. Okay. Now let's go to Blackbody Earth. Let's look and see what the temperature is of the Earth's temperature. Yeah, okay. This is the temperature of a blackbody. What's the temperature of a blackbody Earth with an atmosphere that only contains nitrogen, oxygen, argon, which I'll call the air in the rest of this paper, which normally make up 99.96% of the atmosphere and contains no CO2. As discussed above, the climate models are fixed on infrared radiation as the primary source of heating of the Earth's atmosphere. They ignore conduction and convection, which are considerably more powerful in absorbing and transmitting energy in the atmosphere. Even without any greenhouse gas and gases, the gases will heat by conduction at the solar heated surface and then convect upward, the fact that the modelers ignore when discussing the heating of the atmosphere. For example, let's put it in sunlight. Over here is a tank of nitrogen. A cylinder of pure nitrogen at 1 atmosphere only heats by conduction, direct contact with the metal walls in the cylinder, since the nitrogen is completely transparent to infrared radiation. The gas will reach thermal equilibrium by convection and diffusion. The temperature of the gas inside the cylinder will be room temperature and track it as room temperature goes up and down. This is also true for the other atmospheric gases, oxygen and argon. Another example of the power of convection is a ceiling fan, which we're all familiar with. Ceiling fans standard in many homes and businesses to make rooms more comfortable in hot weather. No one depends on the heat radiated from the skin for cooling. You never get cool. Okay, now this is an interesting. I'm going to discuss this little slab here on the left, on the right. I don't know my left from my right. A simple experiment demonstrates how powerful convection is. A packet of air, 1 meter on the side, 1 degree C warmer than the surrounding air, and rising at 1 meter per second, which is water's walking speed. You don't feel that on your face. Generates an upward flux of 1 kilowatt per square meter, nearly equal to the maximum solar flux of 1.36 kilowatts per square meter. Vertical convection like this can be seen outdoors on a windless sunny day by using cornstarch, that's baby powder if you have some lying around, as a tracer. There are rising plumes, you'll see rising plumes everywhere. They eventually combine to form powerful thermals that are used for transportation by birds of prey. Next, consider the US standard atmosphere in this plot. The troposphere, where all the weather occurs, extends from the surface up to 11 kilometers. The Earth cools as it moves up with a lapse rate of about 6 degrees Kelvin per kilometer. At 11 kilometers altitude, the water vapor in the air has mostly been removed by precipitation. So the only significant gases remaining in the atmosphere are nitrogen, oxygen, argon, and CO2. Above that's the lowest is the lower stratosphere, which is isothermal with a temperature of 215 degrees K from an altitude of 11 kilometers up to 20 kilometers. Above 20 kilometers in the ozone layer, UV radiation heats the atmosphere via the Chapman cycle. The isothermal stratosphere has exactly the same proportions of nitrogen, oxygen, argon, and CO2 as the troposphere. This implies that if there were no water vapor in the atmosphere at all, that is, no oceans, the temperature would be isothermal from the surface up to the ozone layer at 20 kilometers. As drawn, the isothermal temperature would be 217 K, which clearly would not be true because of solar heating. So what would be the temperature of the atmosphere without CO2 and H2O, but heated by the normal solar cycle? There we go. Well, the surface, this is what you'll get. The surface should be thought of as the heat exchanger that converts sunlight into heat that's absorbed by the air via conduction. It also radiates infrared radiation in space that has been generated directly by the sun. Most of the heating of the atmosphere occurs in the vicinity of the hottest point on the surface, which is directly under the sun on the equator. That's the very early, one of the very earliest plots I showed you, where the sun heats up half the Earth, and it's really hot right under the sun. Okay, this is the center of the daylight hemisphere, where the Earth has a blackbody temperature 394 K due to receiving 1360 watts per square meter solar flux. The surface solar flux enhanced temperature drops as one moves radially away from the center until it's in the run out of time. Okay. As the Earth rotates, the entire surface rotates in and out of daylight every 24 hours, driving the daily heating and cooling everywhere. Where the surface is hotter than the air is heated by conduction and then convects up and away from the surface, cooling adiabatically as it rises. This is a fast process because there are no greenhouse gases heat cannot radiate away to outer space and instead will accumulate in the atmosphere. Over time, the atmosphere will eventually become isothermal at a temperature of 394 K. Where the air is hotter than the surface, the air will heat the surface via conduction, and the air will cool, suppressing convection. This is a slow process. Similarly, if the air has become cold from transferring its heat to the surface, it will be heated from above by hotter air, either by diffusion or air circulating downwards and heating adiabatically. This is also a slow process. The consequence is the eventual heating of the surface to the same temperatures as the air at 394 K. Okay. On the night side, the surface cools by radiation. The air at the surface is cooled by contact with the surface, but the cooling suppresses convection and the air stagnates. There's no solar heating, so the surface will radiate its heat away as well. Since the thermal flux varies as the fourth power of the temperature, which I never told you, this surface radiation will rapidly decrease as the surface cools and reduces the cooling rate of the surface. The net result is the Earth without water vapor would have 394 K isothermal atmosphere and surface. The temperature of the profile of the atmosphere would then shift to much higher temperatures as shown here. So this is where you were. We're way down here, and this is where the new temperature would be. So it's going to be isothermal, and then it hits the ozone layer, and off we go. Now, nitrogen and oxygen do have very weak spectral lines that could radiate heat and cool the atmosphere. Because of this, there is a tiny bit of cooling due to nitrogen and oxygen of about 1/4 degree Kelvin per day at the surface. A bit of heating and convection would easily negate this. So the claim that I'm making here that an atmosphere without greenhouse gases is isothermal is not controversial. For example, Hepper and Weingarten come to the same conclusion. Now, so even though we don't need greenhouse gases, let's find out what they would do. The standard approach for understanding the effects of greenhouse gases is to analyze the spectrum of its atmospheric radiation using the equation of radiative transfer. This is rather limited since it does not include the 99.96% of the air that contains most of the energy and emits no significant radiation. A better understanding of the atmosphere is to compute the total energy in a mole of air about the volume of air in a basketball. Although I've shown that the atmosphere is normally hot and there's no need for CO2 or any other greenhouse gas to warm it, it's an interesting exercise to understand if CO2 warming is even possible. And even so, what is the mechanism? The standard approach for understanding the effects of greenhouse gases is to analyze its spectrum of atmospheric radiation using the equation of radiative transfer. This is rather limited since it doesn't include the 99.96% of the rest of the air, which contains most of the energy in the air and emits no significant radiation. A better understanding of the atmosphere is to compute the total energy in a mole of air, the volume of air in a basketball. This is something that chemists use all the time, very useful here. Each gas in the air has its own molecular specific heat at constant pressure. The amount of energy needed to raise the temperature of a unit mass of gas by 1 degree Kelvin. For each air molecule, this can be calculated for the number of degrees kinematic degrees of, this can be calculated from the number of kinematic degrees of freedom plus its vibrational degree of freedom. Every molecule has 3 translational degrees of freedom, molecules that shape like a baton. Nitrogen, oxygen, and CO2 also have 2 rotational degrees of freedom. You can see here and here. The rotations along the axis have no energy. And molecules like CO2 and H2O also have vibrational degrees of freedom due to their internal vibrational states that are responsible for emission and absorption of infrared photons. Collisions between an IR molecule and any other molecule can exchange energy between their translational and vibrational degrees of freedom. This turns heat from the translational degrees of freedom into vibrational energy, and vice versa, vibrational energy and the IR molecule into translational degrees of freedom. So our results of the energy calculations are shown here in the bar chart. The numerical values of the fractional components are also shown in the table. As can be seen in the bar chart, nitrogen and oxygen contain almost all the energy in the air, in a mole of air. Argon makes a small contribution to the energy, while CO2 is negligible. Now, if we look at the table, CO2, there are a total of 8,600 joules of energy in this mole. Only 4 of them are due to CO2. This actually has 2 components, which are seen, you can see in the bottom of the table. About half the energy is contained in its kinematic degree of freedom, translations and rotations, and the second half is due to the vibrational degree of freedom that has to be calculated using statistical mechanics and quantum mechanics. Not too many people in the audience are going to be up for doing that one. All right. If you get the paper, I'll show how to do it. The CO2's 2.5 joules of energy in the kinematic degrees of freedom are sensible heat. That is, they contribute to the temperature measured by a thermometer. The 1.9 joules of energy in the vibrational degrees of freedom store heat, but do not store energy, but do not contribute to the thermometer reading. This means that since the vibrational degrees of freedom stores heat, it requires extra energy to maintain the temperature of the gas. It does not raise the temperature of the gas. Climate world. Okay, this is where we're going to start comparing what the climate world modelers claim and what I've been discussing. All right, the climate models focus on radiation emitted and absorbed by the greenhouse gases to analyze the dynamics of the atmosphere. This is summarized in a version of what's called the Trenberth diagram. Here's an old one for 2009, but there's others floating around that they all look about the same. Within a few, plus or minus 5, all the numbers are about the same too. On the left side of the diagram, it clearly assumes that a very cold Earth with very low, assumes a very cold Earth with very low incidence radiation plus radiation fluxes that move up and down in the atmosphere. The clouds will reflect sunlight out to the space, as does the surface. The remaining incident surface flux of 160 watts per square meter on the left side is quite small. About 70% of the flux in the back of the envelope calculation previously. This would imply a temperature of 231 K, even colder than the 255 Kelvin of the back of the envelope. At the center of the diagram, notice that the amount of convection, thermals in the diagram, is tiny, 17 watts per square meter. As pointed out previously, a slight breeze of +1 degree Celsius warmer air moving at 1 meter per second generates a heat flux of 1.2 kilowatts per square meter, far larger than any of the heat fluxes in the diagram. Furthermore, the convection can carry a lot of heat over long distances in the atmosphere. This is unlike the infrared radiation that only heats the atmosphere within a few observable lengths of its source. There are 2 infrared radiation flux streams on the lower left side of the diagram attributed to greenhouse gases. Both of them are at least twice as large as the solar flux heating the surface on the left-hand side of the diagram. There's several issues with this. First, where does the energy come from for the back radiation? In fact, it's nearly as large as the incoming solar radiation of 341. The same goes for the up radiation, the outgoing long radiation. Where does it come from? From the clouds? So unlike the solar heat fluxes on the left side that pass through an atmosphere that is transparent to visible light, the infrared radiation fluxes on the right side of the diagram must pass through an atmosphere that's opaque to long wave infrared light. A gas layer of about 20 meters is enough to absorb essentially all the long wavelength infrared radiation that shines on it. Some other way must create the flux streams. A mechanism like absorbing and re-emitting photons won't work because the emission of a photon from an excited CO2 molecule is isotropic and can't form a directed stream of radiation. Now, radiation from CO2 and also H2O is massively suppressed by collisions of these gases with air molecules, a well-known and extensively researched process known as vibrational translational relaxation. This is the transfer of energy from the excited state of a molecule, vibration, to its kinetic energy, translation. Carbon dioxide molecules, black dots, can be excited from their ground state to an excited state. That's the red dot. Carbon dioxide molecules from their ground state to an vibrational state, red dots, two ways. One, by absorbing a photon, upper left, or two, by a collision with another molecule of any type, the blue, the upper right. Okay, an excited CO2 molecule can relax to its ground state by spontaneously radiating and emitting a photon, as on the lower left, or by colliding with another molecule and transferring the excited state energy to the molecule's translational kinetic energy in the lower left. The rate of spontaneous photon emission is about 1 per second. At the surface, due to the density of the air, any molecule experiences about 1 billion collisions per second, which is the result of in a large population which results in a large population of excited vibrational states plus whatever is due to the photon absorption. This population is mostly depopulated by collisions and only a few by spontaneous emission. The ratio of rates is only 1 photon emitted for about every 100,000 collisional de-excitations of CO2. The radiation from the excited is very strongly suppressed. This also applies to H2O, where the ratio is 1 photon for 10 million collision de-excitations. The upward and downward surface flux radiations on the left-hand side of figure 18 are non-existent because of this. Now, due to the drop in air pressure, the CO2 vibrational relaxation rate drops to about 1 per second at 85 kilometers, far above the troposphere. Satellites that look down at the atmosphere from altitudes above low Earth orbit are well above where the vibrational translation collisions suppress CO2 radiation. At that altitude, there will be observable radiation from CO2 and H2O. There doesn't seem to be any mechanism that I can find that makes the CO2 heat the atmosphere. All right. So let's now continue with conduction, convection. Prior to World War II, the meteorological view of the atmosphere was different. This can be seen in this reaction to a 1938 paper to the Royal Meteorological Society by G.S. Callender, which was an effort to connect the industrial addition of CO2 to the to the air and the rise in temperature, atmosphere's temperature during the previous half-century. Sir George Simpson, British meteorologist, director of the Meteorological Office, and president of the Meteorological Society, made the following comments in a review of the paper. It's impossible to solve the problem of the temperature distribution in the atmosphere by working out the radiation. The atmosphere is not in a state of equilibrium, and it also receives heat by transfer from one part to the other. And second point, the temperature distribution in the atmosphere is determined almost entirely by movement of the air up and down. This forces the atmosphere into a temperature distribution, which is quite out of balance with the radiation. One could not, therefore, calculate the effect of changing one factor in the atmosphere. So in both cases, he clearly invokes convection, heat by transfer from one part of the atmosphere to another, and the temperature is determined. The temperature distribution is determined almost entirely by the movement of air up and down. Okay. And vote for convection. Simpson's comments connect to the discussion of the isothermal atmosphere that I made above. It pointed out there that the radiation emitted by CO2 or other IR gases is too weak to cause any significant convection, which could disturb the isothermal temperature distribution. Adding water vapor to the atmosphere changes this because of its latent heat of condensation, which contributes to cloud formation and precipitation, and not infrared radiation. As pointed out here, by the latent heat of condensation and in freezing, the latent heat of freezing heats the air, causing it to rise as part of the creation of clouds. Okay. Now in the table shows the amount of energy released by the water vapor's latent heat of condensation with the quantum mechanical contribution to the specific heats of H2O and CO2. In both cases, the latent heat is much larger than the vibrational energy, the quantum heat. So in the case of 0.5% of water vapor, it's 10 times what the vibrational energy is, and 100 times what the CO2 vibrational energy is. If we have 2% water in the air, then we have 8 times as much latent heat emitted as in the vibrational energy of the CO2 molecule, and 400 times what's in the CO2 vibrational states. The article in Wikipedia on, quote, Schwarzschild's equation of radiation transfer, aka the equation of radiation transfer, acknowledges the total dominance of convection over radiation in the transfer of heat energy in the lower atmosphere. The author of the article clearly has certified global warmer states. Schwarzschild's equation can be used to calculate the equilibrium temperature change caused by an increase in the greenhouse gases, but only in the upper atmosphere where heat transport by convection is unimportant. This would be at least above the troposphere where most of the weather occurs, but only with cloudless skies, and probably much higher in the atmosphere at times. It's also at an atmosphere where radiation of the excited states of carbon dioxide and H2O are not suppressed by collision with other molecules. Implementing a model of the atmosphere that includes convection requires using computational fluid dynamics to solve the Navier-Stokes equation for the atmosphere, a very difficult problem. In fact, as pointed out in section 1, the model used parameterization to model clouds and rain because they're too difficult to model by using equations. By sticking to radiative processes, The modelers simplify their work since the equations of radiative transfer are much easier to implement than the fluid dynamics of the atmosphere, which are fundamentally impossible to solve in closed form. Even today, with very powerful computers available, aircraft manufacturers use wind tunnels to test the aerodynamics of the latest airplane, just as the Wright brothers did over 100 years ago. The atmosphere is much more complicated. So, summary. Computer models, by their chaotic nature, cannot make any long-range forecasts that are meaningful. Blackbody Earth with an atmosphere that is made only of the three principal molecules, nitrogen, oxygen, and argon, is a naturally very hot isothermal atmosphere. Carbon dioxide or any other radiative gas does not act as a greenhouse that heats the surface by back radiation. Vibrational translation or relaxation acts to massively suppress emission of infrared photons emitted by CO2 and H2O in the troposphere, which means there's no back radiation to heat the surface. There's also no source of energy independent of sun to provide the energy for back radiation. And finally, convection in phases of water vapor have a much larger effect on the atmosphere than radiation by infrared gases. For example, the latent heat of condensation released by the condensation heats the air high in the troposphere and causes it to rise and eventually create clouds. Rising air also drives vertical atmospheric convection weather, as pointed out by Sir George Simpson. The latent heat of water vapor is much, much larger by at least a factor of 100 than the absorbed energy and the stored energy than the carbon dioxide molecules in the air. And that is the end.
Am I right then that you think that Shula and Ott are kind of on the right track then with the stuff that they've put on here? Yeah,
100%. 100%. In fact, they sort of put me on the vibrational relaxation. It turns out I'd worked on this over a number of years, and I had it on a spreadsheet of mine that I'd done 5 years ago. But, what's the Chinese general, Lao Tse, he says, to know and not to act is not to know. Guess what?
One other thing then, what do you think is the sensitivity if we double CO2 from 425 to, let's say, 850? Is it zero effect or it's just a very small effect? Doubling CO2? Zero.
It doesn't heat the surface of the atmosphere. The energy that it absorbs gets sent right back. The only energy it stores is the vibrational level, and that's not an extra source of energy. It's just energy that's taken out of the either collisions, the heat of the atmosphere, or the lonely photons that come drifting through. And there's no extra source of energy there. It's just sort of like a washing machine. It's going round and round. Goes from the atmosphere into these from the kinetic energy into these excited states, and then back into the molecules that excited in the first place. It's zero.
All right. And do you have faith that science is self-correcting and this is going to be the mainstream view? If it takes, it'll take a while, but people will come around to zero.
Oh, man. I don't know. It's such a huge business. It's multi-billion-dollar business. There's so many people that are invested in it. I don't think it's going to happen for quite a while. Did you ever read what's called? Charles Mackay, what's it called?
Madness of Crowds.
Madness of Crowds, yes. And he says men go mad in herds and then walk away one by one, then become rational one by one. There's a very large crowd that has a lot of money invested in this. is going to keep it going as long as they can.
That's funny that you mentioned that, because like 3 hours ago, I was listening to a podcast, Marty Bent and Guy Swan, and they were talking about that very quote about coming to their senses one at a time from that book.
Yeah.
Yeah.
It's an interesting book if you get it. He's got the first one was, well, there's the famous tulip mania in Holland, but there was one in the United States. It was called the Mississippi Mania, something like that. Do you know about this?
I remember seeing it in the book. I can't remember.
It was the French on the Mississippi at one point, and they were selling land along the Mississippi, and it got into it became one of these crazy manias where everybody was buying land and there was no land attached to the mortgage. So a lot of people lost a lot of money.
One last thing is there is no real lab experiment to prove this is true, right? It's very complicated. The atmosphere is complicated. There's no way to simplify it down to some small experiment that will show that what you're saying is true.
Yeah, I'm sure that the chemists could do that. Actually, the numbers that I gave you for, should I back up?
Yeah, if you're up for it, totally up to you.
No, I said for the CO2 that the excited states get very heavily populated by collisions, and then since they're excited, they could go off as a photon, which is a very slow process because it's once every 1.5 seconds, or it just gets hit by another molecule and that de-excites it, and this other molecule picks up the energy and it's back into the heat pool. That's actually measured by some chemists. That's where the numbers come from. If you let me deposit my paper on your website, I don't know if you do that.
Yes,
you do. Okay. I give the reference. There's several references. The other people who do it are the plasma physicists. They have it. I actually have a reference to plasma physicists, and they give there's some crazy calculation. It was first done by Landau and Teller. Do you know who Lev Landau was? Probably
I do not. I don't.
He was a Russian physicist. This is right after quantum mechanics became a really well understood. Just after what's his name, Schrödinger's equation. So it was in the mid-30s, and they calculate. Teller is the father of the hydrogen bomb, so he's the co-author on this thing. But they actually did the calculations from quantum mechanics about this process, and it's an ugly, a cube root of a temperature. So if you look at the reference I give from the plasma physics book, they actually go through and derive it. Oh, it's awful. In my younger days, I could have done it, but not up to it now. So yes, it's a prediction. It's a prediction. It's a prediction from quantum mechanics, and it's measured.
Okay, very good. And then for the people who really want to dig into this, on my Substack, I'll put 3 different things. I'll put the full transcript from this interview. I'll put these slides from your presentation. Then I'll put your whole paper out there. So from the show description, they can go to my Substack and look at all that stuff, because yeah, you have all sorts of references and people can really dig in there. So
yeah.
All right.
No,
so
I'm glad Atten Shula brought that up. It forced me to go back and look at it and understand what was going on. But that's a real killer for them, because there's no back radiation because of it. It eats up all the photons that would have come back and heated up the surface of the Earth.
did you happen to see any of Young Tuition stuff as well?
I've seen the name on YouTube.
Yeah. Okay. I'm just, it's a separate thing as to whether I think he might have some ideas along these lines, but we won't have to worry about that. So
I think he,
go
I
ahead.
think he put up a YouTube saying that the LIGO was not producing any real signals. Do you know about that?
I do not know about that.
No, he said that. Yeah.
Okay. All right.
So,
Anything else you want to say before I let you go?
no, thank you for having me. It was a good exercise. It got me moving in studying this stuff again. Back to physics after many years of absence.
All right. Thank you very much for putting all this work into it. I'm excited to put it online and see what people say, but I'll let you go. Paul Linsay, talk to you next time.
Thank you.
All right. Goodbye.
Bye-bye.